Welcome back, my lovely students. I always feel like being a radio host, I guess, when I start these. All right, so we are actually going to factor normal looking quadratics now. But we're going to be lazy and we're just going to start with a equal to 1. Now, the reason we're doing that is so we can get practice finding the perfect pair. So that is like the weirdest step of factoring these quadratics. Eventually, we're going to use the AC method. We are technically on these. It's just A is 1, so it's the C method. So we need to find a perfect pair of numbers that multiply to the C number and add to the B number. And this includes whatever signs are on those numbers. So remember, this is based off of our lovely standard quadratic here, ax squared plus bx plus c. So when we start talking about ABC, 9 times out of 10, we're talking about quadratics. A is always the x squared coefficient, B is always the x coefficient, C is always technically it's an x to the 0, which is 1, but the constant term is often what it's called. Later, we are going to graph these guys and we're going to manipulate this and turn it into something that looks a little different. And then we'll be able to plot the vertex, plot the next, poof, and we get this beautiful graph. For right now, we're just going to factor them. So these are not functions we can graph right now because these are not equations. These are just the expression, and we are just going to turn it into 2 binomials if it factors. Every once in a while, you get one that's prime. All right, so we're going to practice finding that perfect pair inside the problems. So on a lot of these, like the directions on these will usually say factor completely. That's code for there's an extra thing you got to factor. Let's take a look at number 11 here. I promised you a equals 1. Why is there 4 in front? Because 8 and 60 are also divisible by 4, and we're going to factor that out, and then the numbers are smaller. Always good. But notice also, that's a cubic. We can factor the x out as well. So that's our first step. Factor out what they have in common. And in this case, that is 4x. And then we're going to write down the leftovers. It's now x squared. And then 4 times negative 2 would give us negative 8. And then an x. And then 4 goes into negative 60, divides into it 15 times, and we need it to be negative, and the x is up front. All right, so this 4x, like I said in the last video, sometimes I will just take it, kind of circle it, draw a little squiggly line, and write it down here to say, the answer should see 4x at the front. And then I stop writing it every line because it gets tedious, especially when we get to AC method where it's more steps. I will still write it every line, but I'm saying if you did something like that in your work, I'd be fine with that. I'm actually pretty good at interpreting student work when y'all do weird things. All right, so our perfect pair. So I want to look for pairs that multiply to my last number here, my C number of negative 15. All right, so what I do is I draw a T-table where I can put all the pairs. Now there's a number of ways to come up with these pairs, and after a while you actually get a kind of good, oh, it's going to be this pair. That's fine. Sometimes though you're going to get a number that you're like, I don't know. In which case you just want to look at all the pairs, or if it's prime, so you can say for sure this did not factor. So 1 and the number itself is always a pair. Now in this case, since it's negative 15, only one of these numbers can be negative. So it's either negative 1 and 15 or negative 15 and positive 1. And then we can add those together and see if we get our B number of negative 2. Those are way too far apart, so that's not going to work. 15 only has one other pair. So we got 3 and 5 now. And again, it's either negative 3 and 5 or negative 5 and 3. And if you check what these add to, -3 plus 5 is a +2. -5 plus 3 is a -2. There it is. Now I do want you to note the pairs, when you flip-flop the signs, what they add to is the same number, just with a different sign. All right. Now if it's +15, just check all the pairs because it won't do that nice pattern. But when it's negative, that's when you know you're close. If you're like, no, I want -2, I'll flip the signs. There we go. Now, there's two ways to go from here. We have identified our perfect pair, -5 and +3. So if we're going to do it the long work it out by hand way, which I will still do, we're picking this pair because -5 plus 3 is the same as -2. I am going to change out -2 for -5 plus 3. But since it's -2 x's, I need to see x's as well. So we have -5 x's plus 3 x's. If only one of the numbers is negative, put it on the first one. You will make fewer mistakes. Either you were going to do it fine, or when it's on the second one, people tend to make more mistakes than when it's on the first one. Now, if they're both negative, you don't have a choice. All right, so there's our 4 terms. And like I said before, I'll keep writing it. All right, now I'm going to write brackets on the outside because I'm about to write parentheses on the inside. All right, so this is our 4 terms. So we can do factor by grouping. So x squared minus 5x, because a is 1, all we can factor out of the first pair is x. And then our leftovers are x minus 5. Now the second pair, it is plus, so again, I'm going to put the green in there just to emphasize it. And in this case, 3 is what we'll factor out. And the leftovers would be x minus 5. All right, so now we have x minus 5 in common. We factor again, we pull that ugly out, and the leftovers, x plus 3, are what remains. So remember, this is just undistributing twice. It just looks weird. But if you were doing the distribution where it was a term onto the thing and a term onto the thing, this should look more familiar. All right, so we have 4x, x minus 5, and x plus 3. That is the fully factored form. If you don't have the 4x out front, Alex will get grumpy. Later on, when we have functions like this that we're studying and we're going to set it equal to 0 to find the x-intercepts, if you forget the x, you're going to miss one of the intercepts, and then the shape of your graph is going to be completely off. Luckily, you should have a graphing calculator to help with that, though. All right. And again, if you have any questions when you're looking at the video, like pause it, write it down, email me, come to office hours, ask me. That's what I sit there and wait for, is questions. Save me from having to do other work, please. All right. Number 12. So number 12, it's written this way on purpose, but it's a little silly. So they all have a minus. We do not factor with a minus in front of the squared term. We could, but we don't like doing that. It causes a headache. So whenever the squared term is negative, first thing we do is factor a negative out. I don't want to look at that. Now, since everything was negative, now everything is positive. But if it was only the squared term that was negative, the other two were positive, then this would turn them negative. So where the signs are and the method we use is kind of dependent on the squared term being positive. We could, the AC method would actually take care of it if you don't factor it out. It looks weird. All right, so that means we're going to see this -1 persist through our factoring. Now, because it's only a -1, you can sometimes multiply this back into one of the binomials, and Alex will take that answer. I just prefer you leave it factored with the -1 out front, because when we graph, that's the way you would want to see it. All right, now I want to draw your attention back on 11 here. That perfect pair, remember I said there was another way to do it? This was the long drawn out way, but this is what AC method will look like. And if you're not comfortable with your factoring, you don't already have a way to do it easily, I would recommend practicing it like this. But this perfect pair here is right there. X minus 5, X plus 3. So when A is 1, you can do what I call lazy factoring and skip straight to the answer. Only when A is 1. If A is some other number, go the long route. Now you can search YouTube and there are all sorts of fancy ways, like I've heard bottoms up, 7 up, crisscross, scissor cut, tic tac, there's so many phrases. If you link me the video, I could probably watch it and figure out how to explain it to you if you want to learn it that way. I do understand quite a number of the ones I just babbled about, but we'll see. The EC method is nice because it's consistent. It always works. All right, so our perfect pair, I need numbers that multiply to 16, positive 16. Then I need to find the pair that add to 10. Now, like I said before, if you're having problems finding your pair, 1 and 16, technically, there's also -1 and -16. Since our 10 is positive, though, a lot of people, when they explain this, won't even write the negatives down, but technically that is another pair that multiply to positive 16. And for me, I like being able to write the definitive list. Now later, once you're more comfortable with your pairs, you don't have to write the definitive list. Like, you figure out your pair, you're good to go. You don't even necessarily have to write it down. But this is all the integer pairs that when multiplied equal positive 16. So 1 and 16, -1, -16, 2 and 8, -2, -8, 4 and 4, -4, -4. And the reason I know I'm done is I got the same number, or I got numbers that are real close, like the 3 and the 5. The only other number you'd have to check would be 4. 4 doesn't go into 15, list is done. So you just start at 1 and the number itself. If it's even, 2 and whatever that would give you. See if 3 works. If not, see if 4 works. Usually you only have to go up to about like 8. Unless the number's really big, like 360. That happens every once in a while. Just keep picking numbers. It's usually not the primes though. It could be 10, then 12, then 15, 18. You might have to go to 24. I think that might be the last pair. Yeah. 360 has a lot of pairs. Alrighty, so here, positive 10, bum, 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 there's our pair. I'm just gonna skip straight to the answer. M plus 2, M plus 8. Because the idea is if you can find the pair, answer. Find the pair, answer. Later on, we're gonna find the pair, we'll do the AC method with it because it's not gonna directly equal the answer. It will get us to the answer. But on these, it works. All right, now what's weird about 13 here? Take a sec, look at it. If we were in class, I'd tell you to talk to your neighbor. But since we're not doing formal lecture, this is your, if you have somebody else in class that you talk to, you could talk to them about this. I highly encourage that. Study groups actually work very well. You guys explaining to each other teaches you better than just practice on your own. So, another life lesson from Miss Liz. So, hopefully what you noticed is these are not in order. We don't factor unless that squared term is up front. So the first thing you got to do is rearrange this. But it was written this way because negative 2c squared, if I put it in the middle, it looks a little prettier. It's math aesthetics, they don't always make sense. So negative 2c squared, that 10c up front is positive, so it gets a plus and plus 12. I do not want to look at that negative, and all the numbers are even, so we are going to factor out a negative 2. So that would be c squared needed to multiply back. Negative 2 times negative 5 with the c would get us back to positive 10. Negative 2 times negative 6 would get us back to positive 12. So this is now the quadratic that I need to consider. Now, this particular thing, when 6 is the last number, pay attention. Because whether that 6 is positive or negative is going to impact your answer. And you're going to think you did it just fine and then realize, oops, you picked the wrong pair. So pay attention to the signs here. Double check at the end that the last numbers multiply back to what you had. All right, so let's write our list. So our C number is negative 6. So that means only one of the numbers can be negative to multiply back to negative 6. If you don't notice that and you do positive 6, there's a different pair that will add to negative 5 but multiply to positive 6. So there's not more than one answer here. You just have to be very careful about the signs. That's another entry into the big book of boo-boos. All right, so again, our usual 1, 6. Only one of them is negative. Negative 6, 1. Our other pair is 2 and 3, and there's no other integers in between, so that is the end of the list. But we just have to do the signs. All right, so down here, I could get positive 1 or negative 1. Negative 2 plus 3 would be positive 1. So if I just had plus C or minus C, I'd pick one of those pairs. Since we have minus 5, I want the bigger number to be negative. And you might have memories of your math teachers doing it this way. But they may not have written it out. They may have just talked through it, which is harder to follow. But once you're comfortable with the numbers, it's kind of what you do. You don't all the time have to write out the pairs if you do like a lot of these. All right, so we have our pair. And again, because we can, C minus 6, C plus 1. Factored, done. Now again, if you tried this out and you got minus 2 and minus 3, while those do add to negative 5, they do not multiply to negative 6. They would multiply to a positive 6. So that is the correct factored form for a different problem. It's one of the reasons why I hate 6 in quadratics here. And inevitably, it is a test question every time if I don't get to write the test. Honestly, sometimes even I put it on the test because it's mean like that. So if you ever see a 6 there, like be like, whoa, it's the 6. All right, 14 here, looking a little weird. Yes, this is still considered a quadratic. It just happens to be a quadratic in 2 variables. We will probably not see this in this class, but if you are going to continue on to pre-cal, this may show up. And if you're going to continue into calculus and past calculus, Cal 2, Cal 3, you do see a little bit of having to argue with stuff like this. All right. So for us, though, it just means our answers are going to have S and T and S and T. And we're just figuring out the pair of numbers that would go in between there as the coefficient on the T's. The S's just have a coefficient of 1 because that was their coefficient up there. 1 times 1 is 1. So we're just looking for, this is, even though it looks weird, this is technically still a quadratic we can work with. But we're going to leave it in this form. I could swap and put the 24t squared first, but then that's in the A position. I don't want to do that. So I need a pair that multiply to 24 and add to a negative 11. All right. This is a long list. We may have to move over and make a second list. So Some of y'all may be like already, ooh, I know the pair, go for it, just go. It's fine. Some of y'all may be like, Now, if you don't want to sit here and write the whole list, because you're like 1 in 24 is not going to give us 11, Liz, why are you even doing that? That's true, it's not. So if you want to jump a little further down, like maybe you're like, boom, I know 24 is 4 and 6. All right. So 4 plus 6 would be positive 10. Oh, we want negative. So some of y'all might just sneak the negatives in there. That's fine. I just habitually write them as separate pairs. Negative 10. 2. Like I can't go closer. 5 doesn't work in 24, but it's very close. So I'm just going to go back out one number. So instead of 4, 3. 3 goes into 24. So this should be our good pair. 3 times, and if you don't remember, calculator, 24 divided by 3 is 8. Don't sit there and go 3 times 6, 3 times 7, 3 times, like you'll get it, but it takes longer. Just use the division. But we want it to be negative 11, so we need a negative 3 and a negative 8. And here's where they go. S minus 3t times S minus 8t. There's our factored form. So if I did those like in the box, multiplied it all out, combined my like terms, I would get back to that start. So this is more to show you if you happen to get more than one variable, one at the front, one at the end, this is how the factored form looks. If you haven't seen that before, it can be kind of freaky. And since we're not doing as much multiplication practice as you guys would have in high school because we don't have as much time, like to be honest right now, this is like a week and a half, 2 weeks worth of lecture from high school that I'm shoving into 2 days, 2 class days. I think the lecture videos will probably be longer. All right, 2 more examples where things look a little weird. We're just going to cover it just so, hey, if it looks this kind of weird, you've got an example to run back to. Number 15 here, that p to the 4th p squared. Favorite for tests because these will also very often factor even more. They're going to make use of a difference of squares usually. I don't think this one does though. I think I deliberately wrote it so it wouldn't because we haven't covered that yet. We will. So here, when I have p to the 4th and p squared. So remember, like in our other factored forms, I had c and c, and that's the kind of term that the middle term was. It was 10c, or minus 5c after we factored out the common negative 2. So this c is what we see up front in the binomials. So whatever our middle term, middle powered term, if you will, is what we're going to see in our final factored form. It's going to be p squared, whatever the number is, and p squared, whatever the number is. So now we just have to find that perfect pair because the a is 1, so find the pair, answer. So negative 45, not a lot of choices. 1 and 45 are way too far apart. 4 plus 5 is 9, so it is divisible by 3, and it's divisible by 9. So this is 3 and 15. While not horrible, still too far apart. That's going to give us 12 or negative 12. So we are down to 9 and 5. Make one of them negative. That would add to a negative 4, so flip it up. Negative 5, positive 9. Negative 5, positive 9. Now, if you're having an inkling of, ooh, weren't we supposed to factor p squared plus 9? Doesn't it do something? It does, but it does not factor with real numbers. So when there's no middle term, like technically I could think of that as a 0p in there. If it was minus 9, I could factor it. A difference of squares, perfect squares. But with a plus, it does not factor with real components. When we deal with complex numbers, the i's, square root of negative 1 might ring a bell there. Then this factors with i's. So for right now, it does not factor. Later on, it will factor once we talk about complex numbers and complex roots. We will have a few problems that kind of deal with that. So if that's a thought in your head, good, you'll need it for later. If that's not a thought in your head right now, don't worry about it. Just this is the answer. And then the last one is written for sticker shock. So this is like when you go to the store and you're like, I love this t-shirt. It is awesome. I love this design. How much is it? Sticker Shock. This is written to be ugly and freak you out. I do this in the notes so you get the freak out of the way when you're not taking a test or a quiz. Sometimes I still end up with a freak out question because I don't always get to write all the questions. So fair warning, every once in a while they still pop up, but I try not to do that. I don't like tests to freak you out intentionally. So it looks ugly, but I put it here so it's doable. I'm not going to ask the impossible, I promise. Seriously. Anything I give you, there is an answer. Now, sometimes the answer might be it doesn't factor. That is a plausible answer. Most of the time, though, especially on tests, it's going to factor. All right, so everybody here has an A and everybody has a B squared. So out front, AB squared. And let's take a look at those leftovers, and the leftovers should look far more comforting. A squared plus 14A, and then that whole AB squared is gone, so it's just the number 48. So all we got to do is find the perfect pair that multiplies to 48 and adds to 14. Now see, by now that perfect pair should be feeling like really familiar, like, oh yeah, I know how to do this now. And if you're still a little rusty with it, that's okay. You get into your homework, practice with these, and then it will be a lot more fluid. And I'd recommend doing that and then coming back to the next video because you want to be comfortable finding that pair, comfortable doing factor by grouping, because we're going to put those together to do the big crazy quadratics. So 48 has a lot of pairs, 1 and 48, 2 and 24. It is divisible by 3. 16 times. Is divisible by 4. That is 4 dozen. Not 5, but if there's 12, then it's definitely 6. That'd be 6 and 8. So there's another way to produce the factor tree. If you like completely split 48 into its prime factors, then you can kind of play like these prime factors here, the leftovers here, what are those products? Then you rearrange them, but it gets kind of weird looking because you're rearranging the numbers a lot. And then it can be more awkward to figure out, am I done? Did I find all the arrangements? If you like doing arrangements, that's combinatorics math. You do a little bit of it in statistics, like keep going. It can be a lot of fun. Not a lot of people like it, so it can be an excellent career. But here, there is our pair, 6 and 8. So AB squared up front, A plus 6, A plus 8. There we go. Lots of factoring with lots of life tips. Sorry for all the moving. That is it for this one. Next video will be AC factoring. That is as ugly as it gets. That will do the job every time.